Jim Keravala, the COO of Shackleton Energy, and a gentleman whose first name I like a lot, Dennis Wingo, the CEO of Skycorp. And so what we're going to do today is have some brief remarks from each of our panelists, and then we'll have some questions. But this is not meant to be a hype about satellite servicing. It's meant to take a critical look. What are the technologies needed? What's the state of their development? What is the market for satellite servicing if the technologies were even ready? Would it be, for a satellite operator, perhaps more efficient to simply replace their satellite with a new technology? Or is there going to be a business case where maintaining that satellite, extending its life, makes sense for them? So we want to look at the market and look at the risk and look at all of the elements of this potential new capability. And if it is successful, how will that transform really the biggest commercial market today in space, and that's satellites. So I'd like to begin with my colleague Ben Reed from Goddard to start us off. Ben.
Thank you, Dennis. I am required by NASA headquarters to present slides in PowerPoint format. I'm also required to stand up while I speak to these slides. So I'll have to oblige my civil servant bosses by doing those activities. The previous panel was excellent. I very much liked Carissa's comments when she said that when an entrepreneur has a vision, their vision is often that the world is going to change. And it is then the entrepreneur's job to convince everyone that that change is possible, and here's how we're going to do it. So we have a vision of the world changing, the on-orbit satellite world changing, and it is going to require you all to come along with me on this journey. So I will lay out what that vision is, what the need is, the roadmap to get there, and I will touch briefly on some of the challenges that we envision, some of the hurdles between here and there, and briefly how we envision tackling those. So I was asked just to put together a couple charts, and a couple in NASA speak means at least 8. So I'll try to do that. I am not going to take a deep dive into the history of servicing, which I could. I'd love to do that for a couple hours up here. So if any questions come up about the history of servicing from Apollo through Hubble and ISS, I'd be happy to take those answers. But you all are a well-educated audience in the realm of satellites, so I did not put those charts into the package, or more accurately, I took them out. So I have one chart on the market. I don't know if any of my colleagues go into the market. Jim goes into the market. Dennis, you go into the geo market as to how large it is. Okay, good. So I won't spend a lot of time on this, and we'll see if 3 sets of charts made independently agree with each other. That'll be interesting. So I'm an engineer by training. I spent 12 years working on the Hubble Space Telescope on training astronauts, developing the new tools and instruments. So when you hear me talk about economics, take it with a grain of salt, but I do have references at the bottom, so you don't have to take my word for these numbers. So you see here we have roughly 400, and these numbers are a little bit dated now, it's more like 430 now, satellites, operational satellites in GEO. 430 operational just in GEO. So that's the market we've been focusing on, is those. Why? Because the orbital dynamics are the most favorable to a multi-sortie servicing mission. The ability to get from one client to the next client to the next client without having to get up a whole new load of fuel makes the GEO belt a logical place, I assert to you, to start off the paradigm for a tow truck services in orbit. So with 430 satellites up there, the breakdown is roughly 280 privately owned and 150 owned by various governments from around the world. 18 satellites, new satellites are launched to GEO every year. Every year, 18 just to GEO alone, more than one a month, just to GEO alone. So this is a thriving hub of activity. I guess it's more of an annulus of activity. The global revenue is in excess of 100 billion. So this market is not dead. They are not hurting, but you know what? With fiber optic cable being strong around the world and being able to carry so much of the bandwidth, the need of the global community, I think really that is where the GEO community is focusing their efforts on how do they combat the ever-growing loss of market share to the fiber optic world. But they are still quite healthy at 100 billion plus. So 600 to 700 million in annual insurance claims. So this is a very variable number, if I could use that awkward phrase. Some years, the annual insurance outlay to the GEO market is quite small. Other years, it's in excess of $1 billion. So this is an average, composite average of 10 years worth of data. It really just goes by the fates, whether there's a satellite left off in the wrong orbit, there is a deployment anomaly, there's contaminant in the propulsion system, which left AEHF stranded, for example. So anyway, I think you'll agree with me that there's a significant untapped market. The question is, how do we go about tapping that market? What are the hurdles? And what are the benefits? So, what could satellite servicing deliver to the GEO market? Well, what do fleet owners and operators want? They want mission resilience, right? If you have a bird up there and it has a sudden loss of power, or you have a launch anomaly, are they dead in the water? Do they lose customers that had signed up for services? They don't want that, right? There's significant competition between all the satellite GEO providers, Intelsat, Eutelsat, SES, Asia Broadcast Satellite. Right? If any one of them stumbles, there is plenty of opportunity for their competitors to pick up that need to fulfill the customer's requirements. So what they want is mission resilience. And the ability, the capability that satellite servicing can offer them is flexibility to launch half empty. So you have a new, you want to get up a lot of transponders, you want to get it up over Asia, but you don't want to have half of your satellite's up mass be propellant. Right now, going to GEO, half of the mass of that bird sitting on the launch pad is propellant. Wouldn't it be great if 10% of it was propellant and 90% was money-making transponders? Well, that doesn't work, because if you want to stay there 10, 12, 15 years, you're going to need more propellant to be able to do it. So you launch half empty. You get up there, everything works, you got the customers, everything's hunky-dory. You call for services, and somebody shows up, and they give you more propellant. That's the vision that we see that servicing can bring. Greenfield testing. Is Southeast Asia ready for C-band or L-band services? I don't know. So let's get a bird over there and see. Let's float it over there. I don't want to have to raise the capital to build a completely new bird, $250 million to get it built, launched, to get there, and then find out we only have 40% of the transponders leased. So let's float one over there that was at end of life somewhere else, see if it works. If it does, we leave it as a placeholder, and then we raise the capital to get a new one up there. So I'm not going to go into, well, just talk about one more. On-orbit failure analysis. For the manufacturers of the world who produce these birds, when there is an anomaly in orbit, they get telemetry to the ground from their bird, some temperature data, some pressure data, what does the power look like, and that's about it. Hardly any of them, or I'd assert to you, none of them have a camera pointing at themselves to say, hey, what happened with that deployment? Was it FOD in the launch vehicle? Maybe we should sue them. Maybe it was our own design. Maybe the cable jumped off. Maybe it was something else. Maybe it was MMOD hit. Who knows what? So if you had an inspection satellite that could provide this imagery to the ground, it potentially could save them tens or hundreds of millions of dollars in correcting the wrong problem. So investors, it enables a new industry, a new location where we can get a high rate of return for the satellite servicing, because once you have a bird in orbit and you've got a full customer load on it, Now you're talking some money, right? One bird over 10, 12 years can easily generate over $1 billion in revenue for that owner-operator. And the insurance industry. I haven't seen any of my friends from the insurance industry here today, but I know a lot of them quite well, and they are very encouraging of us, because if there's a way that they can mitigate some of the claims that get turned in, it helps them, it lowers the cost. For new launches, it lowers the cost to you, the recipient of these services, because the total cost to do business has gone down. So, what services am I talking about? I'm talking about a robotic vehicle that can perform one of, or any of the 5 R's you see here. Remote survey, we talked about that, the ability to inspect a satellite. Relocation, if you've got if you're a general and you've got eyes in the sky over Iraq or Afghanistan, which they might have, I don't know. They might. No? North Korea flares up. North Korea flares up. So what do they do? Does a general move a set of eyes over to North Korea? Well, maybe, but if they simmer back down again in a month, he's wasted that. He has used that propellant where perhaps he wished he hadn't have used it if they simmer back down in a month. And so making decisions whether to move an operational asset to another location, that's a big decision. Because once you spend that prop, you can't ever get it back. But if you could call for somebody to give you relocation services, it might give that fleet operator flexibility. Refueling. Talked about that, the ability to give a satellite more fuel if it had to use its own station-keeping fuel to get to the right orbit, or if it had an anomaly, or if you got a 10-year-old bird that's running out of fuel, you want to make it last 13 till you raise the capital to get up the replacement asset. And I'll talk about the technologies that enable these in just a minute. And then repair. You want to snip that cable to allow the solar array to fully deploy. You want to push that thermal blanket in so the reflector can deploy. Simple repairs like that. I'm not talking about digging inside, pulling out the flight computer and resoldering down a capacitor. I'm talking about simple repairs on the outside, which, by the way, we did with astronauts on Hubble. Not solder replacement, but pulling out printed circuit boards, but we're talking stuff on the outside here. And then component replacement, bringing up a new avionics box, bringing up a new box to jack it in from the outside to augment or supplant or replace avionics services inside the bus. So we've envisioned a public-private partnership to execute this type of mission, where NASA does the hard stuff, it does the front end of the bird. Here you see a notional bird doing robotics refueling of this client, but the payload from, but the spacecraft bus from there back is quote-unquote the easy part. That would be bartered with the U.S. government for free in exchange for use of the bird after in orbit. So we very much are in the vein of public-private partnerships for this first mission. Now, there's risk involved. These are the hurdles. So I'm not going to go into detail with them because I'm probably way past my time already. There are political risks and license issues. There are international treaties. We've thought about these things. I can't say we've licked them all, but we've thought about them, and we've got a plan in place that would help to buy down these risks, that would allow a private venture, a private company, or consortium of companies to partner with the government. There are business risks. This is an unproven market. Well, it's forums like this where we can engage the community to find out what the needs are, what their anxieties are, to knock them down. There are technical risks. The biggest one is, oh, by the way, Ben Reed, of those 430 satellites in GEO, not one was designed to be serviced. I love challenges like that. Wait for the next couple of charts. So we realize that there is still hurdles to be overcome. Our job is to continue to chip away at them to make this viable to a commercial partner. So, the technology risks. We have a robust technology campaign underway, and that campaign is tackling various fronts, and these are 5 of the biggest fronts that we are tackling concurrently. On orbit right now, on the space station. You heard Bill G talk about the ISS as a test bed for technology development work. Well, by golly, he's right, and that's where we are. We've got this box right here, a meter by meter by meter cube on station right now, where we are proving that the technology exists for on-orbit refueling. Then in my talk, you will see a website. You can go learn more about this, and I presume everybody bought decals to hand out of their program to the audience? No? Well, I've got some decals here on the back. It tells you more about the robotic refueling mission. Advanced tools, we've also got those on space station, developing this technology. High-speed computing that can handle the algorithms to do autonomous rendezvous and capture, we've got a D here, autonomous rendezvous and docking of a spacecraft not designed to be docked with. And then the algorithms and the robotics and the tools to perform autonomous capture. So we are conducting a campaign in zero-G airplane flights, on ISS, in neutral buoyancy tanks, and in our lab at Goddard to knock down these technology hurdles. And I'd love to talk to you for 2 or 3 more hours about this, but maybe another time. So, just a slide here on the robotic refueling mission. So as I said, it's a meter by meter cube. We have 4 advanced tools and several adapters to work with those tools. We are on one of the external platforms that was talked about in the last panel on Space Station. And here is the Canadian Space Agency's SSRMS, and then it is holding Dexter, who is picking up our tools to perform the work. So this is a joint collaboration with CSA, our very good friends and international partners with ISS. And the video that you're seeing looped down here in the bottom is the final image from our refueling demonstration. So we have, prior to this, cut the safety wires that were holding on 2 separate caps, totally different diameters and geometries, those 2 caps, with our tools. We then used our nozzle tool to thread onto and then open up this valve. We then transferred in ethanol. There's a simulant for hydrazine. And then we leave behind this quick disconnect with the client as a secondary seal to help assure that there's not going to be leakage after we do so. And there's a small amount of trapped volume of ethanol between the seal in here and the seal right here. And that is the ethanol that you see sprayed out here in the vacuum of space when we withdraw the tool from the quick disconnect. You see a drop lands on the lens right here. It gets dark and then it goes light again very briefly. If you look right here in the image when it... Pretty neat stuff. So, while I do care about venture capitalists, entrepreneurs, opening up a new market, I also care deeply about getting humans to Mars. And I'm selfish. I want both. And I think that is a logical path to take, that we launch a robotic servicing mission to GEO, we kickstart that industry, and then NASA never does it again. Never, ever does it again. Because you know what? Commercial industry will pick it up. And when I need a weather satellite service, if I ever do, 10 years from now, we pick up the phone, we place an ad on the street that says, hey, we're willing to pay $10 million if somebody will go give that weather satellite a little bit more juice. And then the private sector competes to do that, lowering the cost to the taxpayer. And in the meantime, we at NASA have used this technology to help human exploration, to robotically replace instruments in observatories the way astronauts did it so expertly on Hubble, on Solar Max, on Westar, Palapa, on Skylab, on ISS, on orbit assembly, so we can go way out to Sun-Earth L2 and construct a monster observatory. So there are so many things that NASA can do with the technology. So we kickstart this industry, God bless America, and then we go help astronauts land on Mars. What could be better? Thank you. So, although we might appear confident, we still need more friends on Facebook. So I encourage all of you to go on, like us, or whatever you do to bump up our numbers. Thank you.
Thank you, Ben. That was a very good overview. Next, we're going to introduce Jim Armour from ATK.
Okay. You
want to stand up?
No.
Okay, all right. So, does this mic work?
It does. I just have to turn it on. Testing 1, 2, 3. So, during my media training, I was told never to follow animal acts, but that was pretty good, Ben. Last week, is Carissa still in the audience? Carissa asked me to do a panel on the Hill on wicked cool technology. And it forced me to stop and think about where we were headed in our commercial satellite servicing. And I've decided, upon reflection, that I'm not after wicked cool technology. For a commercial business, you need sweet, simple, low risk, easy to control, reliable technology to do wicked cool missions. And that's where Ben and his organization has come in. They've really helped develop a lot of those wicked cool technologies that can be transitioned to commercial industry, and I'll sort of end on that note as I go through my comments. So let me get some of the standard stuff out of the way. Next chart, I guess. I'll hit the button. ATK formed a joint venture called Vivisat with US Space to become a commercial space logistics company. I'm not going to dwell on the text there, but basically we've envisioned a mission extension vehicle, the MEV. We're offering an electronic propulsion jetpack, basically, that docks to geostationary communication satellites that are low on fuel or have other orbit difficulties, and provide them station keeping and station keeping correction for as long as the client wants to lease the service. So if you've got basically a good satellite that's out of gas, you can dock to it and we will do the orbit maintenance or correct an orbit. So what's the business case here? Well, I think Willie Sutton said it best when he asked why rob banks. It's where the money is. Geostationary comsats are where the money is. If I can go to the next chart here. As Ben said, there's about 400 operating satellites in GEO, and there's about 280 operational comsats in GEO. These are hundreds of millions of dollar assets. They got 15-year design lives. This slide just shows the number of them that are within 3 years of normal retirement. So we've done a look at it, and you don't need to look at the numbers because they change pretty much every month, depending on how the satellites are doing in orbit. For extending on life orbits, for whatever reason, reduces the client's capital expenditure and gives them far more fleet management options. And I will talk more about this offline out at the ATK table if you want, but there's a lot of customer benefits. Improves their capital efficiency. It protects their franchise if they're going to have a gap in one of the slots that they have. It drives asset value. It gives them a flexible mission link. It can activate new markets. There's a number of things that you can do there. But there's a larger vision here too, which is mostly what I want to talk about. There's already, we've mentioned the word infrastructure in the previous panel, but there's already what we think of as major logistical nodes operating today. The International Space Station in LEO is obviously one of them, the geostationary belt. There's a host of systems out at the solar L1 location and more that are heading in that direction. We're going to put a big system like Hubble, it's called the James Webb Space Telescope, out at lunar L2. Are astronauts going to go out and restore it when it needs to be upgraded? Well, I think we want to have commercial capabilities available to service those logistical nodes, whether they're on Mars or the L1 or the dark side of the moon. Is there a dark side of the moon? There's also there's a lot in this room even of bold commercial space exploration and more importantly, space exploitation missions. We saw the Bigelow habitat. I know they don't want to stay connected to the International Space Station. They want to, evolve their locations, and they probably will need logistics support wherever they go. We mentioned deep space industries and planetary resources that hope to do commercial mining of asteroids or other planetary bodies. The Lunar X Prize talked about robotic lunar lander capabilities to get to and from the moon. And there's even more commercial enterprises looking at warning for solar weather, solar storms, even inside the L points, heading towards the sun. Sunjammer is the mission I'm thinking of. So, where do we want to go? Wherever you go, you're going to need a supply chain and maintenance of principal mission spacecraft and facilities. Well, what do I mean by logistics? I mean, number one, transportation. You can either carry stuff along, you can schedule resupply, or you can pre-position stuff, whether it's fuel or materials. The second part is revitalization, and Ben has already talked a little bit about that. Repair, repurpose, refuel, maintain, restore, pick your favorite R word there, but basically revitalize the asset or renew its mission. Third is assembly and construction. Make something where the whole is greater than the sum of the parts. And there's a couple other parts here that we've sort of bundled under hosted payloads, which is data collection, sensing. You can either put a sensor on these systems and look outward, or the way we look at it is you put packages on it that look around where you are, a database of working knowledge of the environment that we are working in as a business. So archiving that data for others to use who are going to operate in that logistical environment. And then when you go to outer space resource exploitation, where you're talking about in situ creation of value, mining and transporting that material to processing locations, or using collected matter to create new stuff like fuels, or the 3D printing is a good example. You can create stuff right there in space. So we as Vivisat, a commercial company, hope to grow into this solar system-wide logistic company. We intend, and you can see in the middle part there, not just to stay with the simple Docker to a commercial comm set, but slowly, as each vehicle we develop, add more and more capabilities, a robot arm, refueling, et cetera. Now, this is going to take a while, and I'm counting on my partner Ben here to press the edge of technology so that I can transition that into my logistics company. Ben showed a few pictures of it. By the way, we've done cost estimating for even growing that capability too, but talked a little bit about the technology of today for logistics. You see the power grip tool there, a lot of stuff that Ben's organization has made, and for the record, ATK has a lot of engineers as part of Ben's team building and developing these capabilities. But ATK also builds the end effector tools. Ben had the same picture in his few graphs about the tools at the end of the robot arms that do things. We've also had a lot of content in designing and building surface and subsurface mechanisms for the Jet Propulsion Lab, and a lot of our tool development is walking around on the moon, on Mars as we talk. So it's given us a lot of confidence that we can grow into this larger robotic logistics mission. So what is the technology a commercial firm and a new business area needs to use? Well, basically I'm after dirt simple stuff. I'm trying to minimize risks, minimize my costs. Our initial MEV is as standard and simple a bus as we can make it. The docking tool is as simple as we can make it. So what's the point? The business case has to close is the point. Industry will use new technology, but it's probably not going to be the exotic, expensive, finicky stuff. That's where I need the government to be pressing back that edge of technology. DARPA is also doing some pretty exotic things with the Phoenix mission that we're involved in. So message number one, please continue the development of the technology that can be spun off into industry, and continue to find ways like the public-private partnerships to allow commercial access as that technology is developed. I'm convinced that commercial logistics will evolve on its own to support commercial space activities, but if the U.S. government wants to help it along, that's okay. Bill G. said, first do no harm in his comments. I agree with that. We should use commercial services as they're available. We should use the Space Act, either funded or non-reimbursable, to stimulate the industrial base in the directions that the government wants to see it. So what might be in the way today? A couple of political things to say here. Other than lack of budget, ITAR reforms. If any of you aren't aware of the ITAR reforms that the administration has gotten through Congress, please encourage those along. That was a major milestone, and now we're in the rule implementing phase, and we're making a lot of good progress there. Alas, there is one rule in there that precludes export of satellite servicing. So that's not a showstopper for us, but it is another constraint that the rules have put on startup companies like Vivisat. Also, the United Nations treaties or other conventions that limit commercial exploitation of space will really kill a lot of our mutual interests there, and we need to sort of continue to be part of the conversation there. So Vivisat Mission Extension Vehicle is what we consider the first baby step in a space logistics company and an infrastructure that will support all the commercial and government ventures as we populate into the solar system. I've got a few logos on here. There's room for every government and commercial logo. I'll take one of your stickers, Ben, and put it on there. If you don't see your name on here or your company on here, please come talk to me afterwards, and we'll make sure that you're included. That's all I've got, and I'm looking forward to the discussion.
Another Jim. Thank you.
I'll take the podium here. So we've had a couple of great talks on the technologies and the detail of implementation for on-orbit servicing. But for the last 40 years or more, we've really struggled as an industry to identify the critical mass of business and market case, where the customers are, that will really allow us to close an end-to-end chain of supply and to supply-enabled demand. So Shackleton Energy Company has taken a step back from this immediate problem. When we're looking at propellant depots and refueling and on-orbit servicing and facilitation capability, we've looked at the real reason of why would you want to have it. Okay, we have geostationary markets in place, and that is an interesting, significant market. But in reality, it is actually only a small market. It is a small market with a potentially finite window of 1 or 2 or 3 decades. And then it will morph into something else and change and adapt. How do you meet that changing and adapting requirement of the market? As we've seen with Iridium and other business models where the infrastructure timescales of development are so long that terrestrial solutions and alternative solutions can overcome your business model before you've had a chance to actually implement and execute, we need to accelerate our ability to meet market demands, meet the customers, and actually undertake something. And this happens to work if you take a problem big enough that goes far enough where you converge to a marketplace that doesn't yet necessarily exist and bring together a set of capabilities that aren't necessarily in place. And if you're careful and if you're smart, and if the net present values and the cost of capital acquisition of your entire program at each step of the way fit the model of investable programs, then you basically have a new frontier opening up with your availability to meet demand. Shackleton Energy Company is meeting that demand and building that model. We are establishing operations in space and on the lunar poles to extract water ice from those regions and bring that back to low Earth orbit for utilization as cryogenic propellants for in-space utilization in near-Earth space and for far-field exploration, all on a fully commercial industrial basis. Closing the loop, both technologically, programmatically, and in the business model, is key to ensuring that the next 40 years are not a repeat of the last 40 years that we've undertaken in the space sector. We've had brilliant pieces of technology and engineering undertaken, both by governments and commercial organizations. But if you look carefully, our ability to optimize and repeat efficiency and capability is just not there. If any terrestrial industry operated the way we undertake the space sector, we would have some real challenging economics going on. So if we look at what the gap is, and really try and understand how we can close that, and how the ability of servicing and the ability of propellants in space with low-cost fuel can change the entire paradigm of access to space, we have to understand what's happening with space. We have very clear transport capabilities to low Earth orbit. We have destinations, far-field destinations, that are really not yet realized, and we're not able to harvest, exploit, and utilize them for the benefit of all. So in the middle is this gap of energy and servicing capability. So we have launch vehicles that take us to low Earth orbit. We have destinations, latent destinations, that offer extraordinary opportunities for business, for expansion of humanity, for exploration, for undertaking a number of human directives and human initiatives that we have undertaken for the last 50,000 years or more. We need to maintain and open that frontier for our economy and our civilization and culture to continue to thrive and not remain in a closed system. That energy is the real paradigm buster in the middle between those two facets. If we create that on-orbit and in-space and on-surface infrastructure and capability, and we do it smartly enough, and we utilize the best of terrestrial operational capabilities in technology development, in programmatics, in financial management, and meeting the customer requirements without kidding ourselves on what real markets are, then we can close that gap, bring in the investment capital we need without drawing people's money into a sucker's gap by clever marketing or creating a hype cycle that once again then falls into another dormant cycle. If we close that gap intelligently and carefully, we can really undertake something and make a real change to our future in space that has not been undertaken in any way before. And we know, without going into this in detail for this audience, but just to re-emphasize the point, the real reasons why we talk about on-orbit servicing or depots or access to energy in space is because we live on this beautiful planet with a very significant mass and a significant atmospheric envelope. Whatever we talk about in the future, our current technologies, it's important to really keep this in mind, our current technologies require so much propellant just to get into low Earth orbit that we're looking at 85% of our launch vehicle mass being propellant and its infrastructure. When you think about that, that's an extraordinary amount of asset to keep launching up all the time. And then when you add to that, not only is 85% of our launch vehicle propellant mass into low Earth orbit required just to get it there, when you're there, as Ben mentioned, when you're there, going into GTO, translunar or trans-Mars injection, just adds even more propellant requirement. The more you want to do in space, beyond LEO, the more propellant it takes. And the more propellant it takes, the more you have to optimize your systems for mass efficiency. When you continue to optimize for mass efficiency, you increase either you increase your risks or you increase your program and mission costs due to extra cycles of QA engineering and assurance. and you get into a vicious cycle of programs that become basically unaffordable, unsustainable, and unrepeatable. If we're to break that vicious cycle, we need to establish rapidly in-space propellant depots and on-orbit servicing capability. And I'm not talking about a piecemeal incremental development. We need to take a step back and look at the real business model. Where are the real markets, and how can we build to scale so that that initial investment, whatever its size, makes full business sense on an industrial scale. And by establishing propellant depots in space, we can lower the cost rapidly of in-orbit infrastructure and in-space infrastructure. As Shackleton's business model, if we then close the lunar supply loop and bring in water from those polar regions, cryogenically split that into liquid oxygen, liquid hydrogen, combine that with a servicing capability and a capability for human presence, and within 2 decades of that program operation, have the ability to create structures of materials by the mid-2030s of heavy materials and structures. We can start to then bring in just the complex components that we need from the Earth's surface and build very large-scale vehicles and programs that can then benefit life and markets on Earth. And so, taking that step back, we need to have an end-to-end architecture. If you try and build a chain and you've got a weak link in any of that chain, whether it's your supply chain or your market model or your customer delivery capability, your business will fail. So in order to close that chain, we have created a multi-stage program of increasing milestone opportunity and decreasing risk as we push forward, enabling full assays to take place on the lunar surface, building up both a robotic and a human-capable infrastructure in space, utilizing common technologies that are built on production line manufacturing capabilities, not single units built piece by piece, but changing the very nature of how we build vehicles in space. And then enabling those same vehicle builds and components and submodules in a component and plug-and-play architecture built around common standards and interfaces, which is vital, absolutely vital. We can increase and build this total end-to-end supply chain, allowing tankers of water to return back to low Earth orbit, transfer their product to the refineries and the depots, and enable customer delivery. The on-orbit servicing element of that kind of architecture now becomes not only a nice to have or useful for creating new markets, industry, and profit, it becomes a vital component of a closed cycle business that will expand out in many ways, as we've seen with rail, aviation, and other heavy industries on Earth. And so when we are looking for the reasons for doing all of these activities and really trying to rationalize and justify them, the only real thing we can look to are the customers and the markets. And if we recall just how expensive energetically it is to get anywhere in space, we have an opportunity by combining propellant depots with on-orbit servicing to effectively create the killer app in space. Because now, when you, as Ben was alluding to, when you can reduce the need to transfer your beyond LEO or your post-LEO propellant from the Earth's surface to low Earth orbit, you now effectively double the effective launch mass of every launch vehicle for complex hardware components. And we can then supply the propellant in space with whatever lower capability system we have, whether it's from the lunar surface, whether it's lower reliability launch vehicles, but we now create a new opportunity to revamp and upgrade our launch vehicle capability without making a single change to our launch vehicles. For the specific complex, for the complex mass in your space vehicles that you are launching, you've effectively nearly doubled your specific launch mass, your launch dollars per pound or per kilogram. And this is the killer app that we can actually achieve if we build that end-to-end system. And on-orbit servicing, propellant depots are a vital architecture of that if we apply that carefully. So trying to stick to 5 minutes, but that's it. Thank you very much.
Dennis Wingo, Skycorp.
Let's see. Jim, I'm not going to run yours. Well, hello. Most folks here know me. I have a set of slides here that should come up in a second. Long time Space Frontier Foundation, long time in the space business, do a lot of interesting stuff. We do a lot of work in the past with space. We do a lot of work today, and we're going to be doing a lot in the future here. And I think it works like this. There you go. Just very briefly, on-orbit servicing has been around for a very long time. All the way back, Werner von Braun had his first patent for an on-orbit servicing system in 1953. What you see here is a space tug. This is a NASA from Marshall Space Flight Center PD in 1970. The one on the right was NASA's telerobotic servicer from the early 1980s, a lot of which, if you take a look, the SPITM that is on the Canada arm on the International Space Station is pretty much the descendant of the flight telerobotic system. But we want to talk about commercial on-orbit servicing. And we started out in commercial on-orbit servicing in 2001. I had a telecom billionaire, many of you know, who came to me and said, Dennis, I am tired of science experiments. One of his science experiments was he had funded rotary rocket. Another of his science experiments, he had bought the Mir space station. So he was well versed in the, let's call it the really bleeding edge of commercial space efforts. And so we started thinking about it, and it was the same thing that Jim from NASA said, and Jim Armour, is where the money's at is in geo orbit. If you take a look at all of the other areas, that's just where the money is. And where we started was with a company called GeoMedia. We actually were going to try to sell the Yamal, the Russian Yamal GeoComsat bus in the Western markets. And at the time, the satellite market, this is around 2001, was just not ready for that. So we came up with, we were sitting with some folks from Aon Insurance, and they said, and we're looking at all of these satellites that were in inclined orbits. At that time, there's dozens of them. And we're going, you know, and the transponder prices are through the floor. And we're going, you know, if we could actually keep these satellites in GEO, they could have their normal rates, and the satellites would still be much cheaper. So we came up with an idea. We came up with this concept. We called it, this is the orbital recovery, it was called the Cone Express, or the CX-OLEV for Orbital Life Extension Vehicle. And since we were already looking at the ITAR problems, we set up shop in Europe. Interesting way of having to do business when you're an American over a technical project in Europe, but we were able to get through the ITAR issues. And Dutch Space was our prime contractor, along with Swedish Space, Kaiser Trady, Senair. We had several European, let's call them Tier 3, Tier 2, Tier 4 contractors working on our team, and we came up with the CX-OLEV. And it was a good system to start out with. We were supported by ESA. It was a public-private partnership under what is called the Artis 4. We had shared funding from ESA. ESA put in about $4 million, and we put in our money. The German space agency, DLR, put in additional funding. And so it was a true public-private partnership, because ESA has as a core mission, even more than NASA, is job creation in the industrial sector of aerospace in Europe. So they have very, very extensive programs in this area. But the shortcomings, we went all the way through, we call it the first baseline review. We were at S-Tech. We passed all of our reviews, but we had some shortcomings. It was going to be too costly to be able to meet our market. Our elevator pitch for on-orbit servicing is that for 1/3 of the replacement cost, we can give you 10 extra years of life. And Jim from NASA, basically said it, there's $1 billion potential revenue of a geocomsat in 10 years. So if we can go in and for 1/3 of the replacement cost, give them that extra $1 billion in revenue, as they say, the rest is just negotiation. And when we were there at S-Tech, we had a low-cost launch. We had ex-Arianespace people working with us, and we had really good launch process from Arianespace, the secondary payload. We had the teaming with DLR, the German space agency, with already proven space robotics for the capture tool and the docking to the spacecraft. The day that we successfully passed all of our reviews, and this is another part, this is business. The day that we passed our reviews, we had our customer there. Our customer had signed off on it. Our chief investor was arrested as the largest tax cheat in U.S. history. Kind of puts a crimp on the business plan. But even with that, our customer, Optus, Singtel Optus in Australia, they spent the money on their lawyers. They spent an additional $20,000 in legal fees to go through to a contract for Optus B1 and Optus B3 because they felt so strongly in our business, they saw our technology, and that they felt that we were going to be able to move this ball forward. And that's a strong statement. Now, you talk about customers, that's a customer. So we went on after that, and we kind of reconstituted the team. We changed the company. It was Orbital Satellite Services Limited, and then Orbital Satellite Services AB, with Swedish Space as our prime contractor in Europe. And our system was based on the Smart 1 spacecraft that had launched as a secondary payload on Ariane 5, and using electric propulsion had gone all the way to the moon. So we had a proven bus. We had a proven electric propulsion system, we had a proven contractor, and we kept the rest of our contractor team in Europe, and we kept our artists. Well, actually we didn't. We walked away from the artist funding because one of the things you find, and this is one of the downsides potentially in public-private partnerships, is that, let's say in this case, ESA brought 50% of the money. Well, the complexity of the system went up by 50%. So at the end of the day, it was a net wash. And so we were still working with artists, and we were very happy with our ESA folks, but we kind of restructured to where we drove the requirements. And when you're having a public-private partnership, this is one of our lessons learned, is that the private part of the public-private partnership has to drive the requirements if the public-private partnership is going to bring benefit to the private party involved. If you don't do that, if the other side drives it, it is almost inevitable that the costs are going to go up, and they will go up in such a manner that you may end up being not affordable. So the advantages, it was a lower cost, it was a flight heritage system, we still had a secondary payload, we had some really good launch prices, we had multiple launch providers. Again, we had some very experienced people on our team. The disadvantages, it still was marginally cost-effective system, and the station keeping technically was kind of inefficient because when it's just to the back of the satellite, if you see the little electric propulsion thrusters on the top and bottom, they're inefficient because of cosine losses in some of the actual station keeping itself, north-south station keeping. But it was a much more cost-effective system than the one before, and we had a very good team. We signed 2 contracts. We had over 200 million euros in customer contracts with this system. In 2009, however, because of legacy issues associated with the business and our founding investor of Orbital Recovery in prison, that effort kind of shut down. Well, over the past several years, I've spent a lot of money with attorneys. I've spent a lot of money with business people to take care of those legacy issues. And so today, I am pleased to announce here at the Space Frontier Foundation Conference, the Skycorp Spacecraft Life Extension System. And we take all the lessons that we learned from the OLEV programs, all of the work that we did there, and we've continued to do our design, refinement, and development. And we've been able to lower the production cost of the system by 50%. We have a 40% lower development cost of our system because of some changes that we've made, some that will go into patents that we have not filed yet, so I'm not going to go into them. But we've been able to really beat on the one thing that is absolute crucial, is to cut the cost. And we now can reach that goal that we originally had, that for 1/3 of the replacement cost, we can give 10 extra years of life. And this system will dock with any geocomsat. It can extend the life. It can do the mission to the graveyard. PNAMSat, when a new rule was passed by the FCC determining the graveyard orbit, the PNAMSat at that time said it was going to cost them $400 million just for that, to move their 19 satellites to the graveyard orbit. We're able to do the graveyard orbit. We still have our relationships with the German Space Agency. We still have our very good relationships in the insurance community. And the insurance community is very interested in this system. And so in operational efficiency, we're at about 175% of what we had with the Smart OLEV. And it's still a secondary payload. So this is what we're doing. We're focusing on the near-term market, because if you don't make the near-term market work, all of the really cool stuff you want to do later never happens. I can't tell you the number of meetings we had with satellite operators, and we'd tell them all about our system. It says, yeah, but you know, if you added a robotic arm, if you did this, and we're going, you know, we want to do all of that. And after our first $1 billion in free cash flow, we'd be more than happy to add it. But that was the focus on the business, the focus on reducing cost, and the focus on our customer is what allowed this concept to continue to grow. And I can also say that we do have one signed letter of intent today from a non-disclosed customer in the global GeoSatcom market. So we had a lot of traction out there, a lot of folks like us, and it's a commercial market. As much as the government can help, what the government giveth, the government can taketh away. And so you have to be very careful, and if you do not have a commercially focused business, you just end up being another government contractor, and that's not what we want to be. We love NASA, we do a lot of work with NASA, but at the end of the day, we want commercial space to work, and we want it to happen. And that's my talk.
Thank you very much. So, everyone here has talked, it really comes from the supply side, that we're offering the capabilities to supply these services, and we've discussed the addressable market, the satellite operators out there. You've all talked to the potential market. How does the demand side look at this? What are the trades they see, and what will be the trigger that brings them into the market? Let's just have a quick comment from everyone. Ben, you want to start?
The most vocal proponent on the demand side has been K-Sears and Intelsat. As most of the people in the audience probably know, Intelsat had a relationship with MDA, McDonald Detweiler and Associates of Canada, for services a couple years ago. Subsequent to that, she spoke at a workshop that we hosted at Goddard a year ago, and as the keynote, talking about the fact that she wants on-orbit servicing to bring options to her and Intelsat as a fleet operator. I mentioned in my talk that the insurance market, and I believe Dennis will, he mentioned them as well in his, is one of the strongest proponents for on-orbit servicing. So I've listed a few individuals, and a few companies. I have not listed hundreds. But I think an interesting analogy would be cell phones. I can't imagine when the first cell phones were envisioned that they would, somebody had the forethought to think of Twitter changing the Arab Spring when the first cell phones were imagined back a few decades ago. A more pertinent example would be Dexter on ISS. Dexter and the SSRMS were envisioned to move or use around on the outside of the space station, but demand for Dexter has done nothing but grown. It is oversubscribed. It's very difficult to get time with Dexter because now that it's up there and people see the capability, their imaginations have taken off with what it can do. So there is demand. There's concrete demand from people with money for the servicing. But I think once it's up there, that's when you will really see the floodgates open as to what people can do with it. So I hope that was brief enough.
Yeah, I can't talk as freely about all the conversations I have with our demand side, but it is a demanding demand side. And the conversations are detailed and technical, and they're with regard to their managing their risk with their insurance companies, and they are also, we find ourselves talking more and more with their equipment providers, so the manufacturers of their ComSat system, which, as we've already pointed out, are not designed for satellite servicing, become very detailed discussions, good, robust discussions, which is why I keep coming to, I need as simple a technology as I can get away with to do these missions. But I can't tell you how many times, approximately once every 2 weeks or so, we get a call from somebody that wonders when we are going to be on, are we on orbit next week because we have a problem that we want you to go fix, right? Oh, you're not up there yet? Oh, darn, you know? And so we get a whole stream of demands from the simple to the sublime, and we've really had some interesting and robust discussions with the demand side. And I'll stop there before I get myself in trouble.
So when you're looking at the demand for on-orbit servicing or in-space propellants, you have a certain market, both commercially and governmental. And I'm not talking about governmental contractors, I'm talking about governmental as a customer. The opportunities, if you can diversify, but balance the trade-off of maintaining a focus in what you are supplying and what you are then delivering to schedule to those customers. If you can diversify your markets using the same technology, you increase 5 or 10-fold the number of demand streams that then become available to you beyond the traditional on-orbit servicing that we look at today. So our strategy is actually utilizing some of that synergy and leveraging common technologies and a modular plug-and-play architecture to take similar capabilities and apply them to different markets. And when you do that, the on-orbit servicing segment of that demand becomes a core of a much wider, much more demanding and robust business case and business model. So I've said nothing much there, naturally, but I can assure you we've looked at this very significantly, and there are a number of business streams that integrate.
I can be a bit more forthcoming. We had a lot of fun with the satellite operators around the world. Many of them suggested business strategies for us that were very helpful to us. One of the things they appreciated that we were a commercial company doing commercial space. There are cultural issues in certain parts of the world in doing business with American companies. That's one of the reasons that we were in Europe, and we will continue to have a European presence in what we're doing going forward. But there are businesses, and both gyms made very interesting statements that you have customers who will come to you. Are you up there yet? If you were up there, then we could do X, Y, or Z, which presents the chicken and the egg problem for all of our managements is that, or investors, is that it's the if you build it, they will come. This is an absolute certainty in the on-orbit servicing market. The problem is in convincing management and or your investors to put up the money now for something that could be in the future. This is why for us, having signed customers, and one of our big signed customers was Eutelsat, the second largest satellite company in the world. And so when you have a marquee customer like that on your side, and when you are moving forward, the door starts to open. And every single one of the operators said to us is that when you are up there, the floodgates are going to open because there's things that you can take advantage of in law, there are things that you can take advantage of in the insurance industry to absolutely, it's the exponential growth thing. And it's all there, but what we got to have is somebody somewhere, whether it's in our management at our large aerospace companies, at our national space program, or in our investor community, to make the faith statement like Elon did. Elon had a faith statement that if he built a lower cost launch vehicle, they would come. And look what he has leveraged from that. But he had to put up his own money first. And this is something that Dennis and I have had this conversation, we've all had this conversation. When you come to the party with your own check first, everything else becomes a lot easier. And so that's where we look at it.
So are there any billionaires in the audience?
Jim, you have a question for the audience?
Yeah, are there any billionaires in the audience?
I'd like to open it up for some questions now from the audience, whether you're billionaires or not. It's okay. Please wait for the microphone. And let me do a quick question we had online while we're waiting. Do we need a Swiss Army knife, or should we focus on one or two key capabilities first? Anyone?
Either. Don't wait. Just get something up there.
Amen.
We think, starting with the single blade, and then as you evolve, add more blades to the mix. So it's a growth pattern.
Yep.
Thank you. Do we have a question?
Sorry. I think this is on. Oh, okay. My question would be, since a number of the presentations talk about automated docking and servicing, do we actually have examples of in-space operations where automated docking has worked without human in the loop? Because I know while mention was given to a number of the space shuttle docking and service missions and stuff, I believe all of them had to require astronaut intervention in order to actually capture the satellite.
We have two strong examples of automated rendezvous docking. One was DLR, the German space agency, and the Japanese space agency, JAXA, in ETS-7 in 1998 in low Earth orbit did multiple autonomous rendezvous and docking. DARPA in 2004, 2005 with Orbital Express did the same thing. Now, Orbital Sciences kind of had a bump with DART, but so the answer is absolutely yes.
Yeah, I guess my only comment to that would be, I think it was 97 with ETS-7. That was a very successful mission with JAXA. Orbital Express was cooperative. It was autonomous. There was no human in the loop. They pushed a button and it worked. But the client was not non-cooperative the way that the clients we envision is. So that's why we're spending some of our resources on no human in the loop for clients that were not designed to be serviced.
So there are also a number of trade-offs to the question. What is exactly you're trying to achieve? If you're trying to achieve a specific narrow service opportunity, you could probably get away with full autonomy. We've got mining executives and companies on our team, a number of aerospace companies in the consortium. We have astronauts who have undertaken EVAs. And we built our orbital autonomous systems ourselves that we deployed in extreme environments using SLAM, simultaneous location and mapping technologies and maneuvering capabilities. The trade-off becomes, what is the cost profile you're willing to accommodate to have autonomy in ever-increasing industrialized operations and extreme operations. And there is a trade-off of supervised autonomy that we've come to a balance point as a reference, especially as we go into lunar processing and expanding into hard industrial environments. If you're in a structured environment, autonomy works great. If you go to an unstructured environment, sooner or later, the autonomous system is going to have a failure point. And it becomes increasingly harder for subsequent autonomous systems to really work out that failure point, especially if you're delivering to a revenue schedule. So if you look at oil rig platforms, mining operations, any heavy industry on Earth, there's autonomy as far as you can push it, but you can bet your boots that there'll be boots on the ground nearby to maintain that delivery schedule as necessary.
At Vivisat, I think you have correctly identified one of the key constraints, and we have put a lot of our investment into that. We built a full-scale mock-up of robotics to simulate it. We've got air-bearing pallets for contact dynamics. We've done a lot of investment to minimize the risk on that, working with our first clients to do validation, verification of just that very technology. You are correct, that is one of the risk points. But I think for a lot of historical and the homework that we've done, we're in good position to address that technology.
Okay. Another question? Yes.
Hi, Emily Briere, Duke University, Research Associate at NASA Ames this summer. I have a question for Dr. or Mr. Keravala. I was wondering if you ran into any policy challenges in terms of mining ice from the lunar poles, which technically don't belong to anyone, and selling the ice for propulsion. And I was wondering if you anticipate any backlash as you expand. Thank you.
So I'm going to make an assumption that the background of your question is in effect the access of the commons to the universe and celestial bodies. We have an asymmetry in our regulatory environment and our international nations and makeup, in that not all countries have access to space as yet and the freedom to undertake operations. So the Outer Space Treaty and the lesser ratified Moon Treaty both reflected those desires to control and maintain that balance for various reasons. What we are doing in extracting those resources and harvesting those resources and building that infrastructure is laying the foundation that will bring opportunities for power, for terrestrial fresh water, for a number of benefits on Earth by mid-century as our population reaches 10 billion or more people. And we'll be under severe energy, fresh water, and other resource constraints. It is our duty and our responsibility for those who can see that coming challenge to do what we can to prepare the platform for the next generation that's coming before us, and not to spend another 40 years caught in the mire of regulatory challenges and policy issues. There are those that will quote the letter of the law and the letter of the regulation and say, well, you have to be careful about this and you have to have frameworks for that. It's very valid. We do need those. But all of those frameworks and all of those regulations that we have and the treaties that are in place also allow us to go forward, to expand the frontier and do the best we can for ourselves as a species and a civilization, and not get caught up by our own shoelaces.
Thank you.
Hello. My name's Debbie Wilkinson with the Open Luna Foundation, and I was just wondering, with your on-orbit servicing, that you are servicing quite a diversity of spacecraft that have been, especially with the heritage space, each done independently. Is there enough commonality or standards associated with the way these things are built for you to dock and service them, or have you just found good ways to handle that?
Who'd like to take that? I'm not sure about Dennis's device, but ours is compatible with about 85% of the commercial ComSats that are up there. And we hope over time to evolve it to include more and more. In fact, as I mentioned, we're talking with some of the original satellite manufacturers, and they are migrating their design to something that may be a little more conducive to this in the long haul. But you know, you're talking years. Dennis, did you want to?
Yeah, today there's the launch vehicle interfaces are all common across the entire industry because of the commonality on launch vehicles. And there are common aspects to, like Jim says, about 85% of the satellites, common mechanical systems on the back face of the satellite, and that's what we depend on. Although, what we find out is when you look at a case-by-case basis, there's always variation, so your system has to be flexible enough, yet simple enough to be able to handle the cases that aren't documented. You would think a lot of this stuff is documented, but people do stuff at the last minute all the time, and so you have to have a flexible system.
Agree. And I also want to point out that we're talking about the watershed moment here. What these two gentlemen have in their offerings is services for the existing birds that are up there now. Well, pop quiz audience, how many new birds are going to GEO every year? 18. That's great. You guys are very educated into the GEO market. Well, guess what? The ones that are on the launch pad now, they're probably not going to make any changes to. But as the assembly line of birds going to orbit continues, and with the inevitability of servicing upon us, making incremental changes, putting a couple decals on the back end so you get a stronger signal when your sensors are looking for the client, putting Velcro instead of tape on the blanket on top of your fill and drain valve. These are very small things to do that make it a lot easier to service. So the technologies that we are developing, that they are developing, is amenable to the existing fleet on orbit, but there's some easy things to do to make it even easier as we go forward. And then I think standards will start to evolve. All right, NASA doesn't want to dictate to the GEO market, you must have a ring 18 inches in diameter that looks like this to be serviced. Not by any stretch. But I think commonality and standards will evolve. I mean, how many of you have trouble getting the nozzle to refuel your car when you go to the gas station? Nobody? It's because the standard evolved that people agreed on as to what that interface would look like. And that's the way I think satellite market is eventually going to go.
Unless I try to use diesel by mistake.
Last question.
We have time for one more question. Dave?
Yeah, one of the things that kind of follows along on the standardization discussion, one of the things that worked in the airline industries of the early day was that you had competing airlines looking for the same market, basically. They still managed to agree upon standards, and that was something that really helped to be able to get commonality between vendors for different components. One airline could get a avionics box, communication box for many of a number of different manufacturers. They could swap engines between different manufacturers among different aircraft. You guys are kind of competing here for some of the same business. Have you thought about how you can be able to have cooperation, which this allowed the airlines to do things like even trade assets between them and help themselves out?
Great question. And it brings me back to my website. So we have thought about this, and we were approached by the insurance industry who said just that. Ben, what can we do now to make servicing easier so I don't have to have as large of payouts in the future? So we started an online discussion on our website for a family of aids that we call COSA, C-O-S-A, Cooperative Servicing Aids. And that is to elicit suggestions, comments, feedback from satellite manufacturers, from owner-operators, from the insurance industry, as well as those companies that make technologies, as to what makes sense to standardize. I mentioned a couple, decals on the back end, Velcro instead of tape, but electrical connectors, right? If we agree that we're going to go with a micro D connector, and that's going to be the data power interface for any new avionics box that gets put on the outside. Great. NASA's not going to dictate, but if we as a community come up with this, then the cost goes down because the various service providers can all use that same standard when they go to orbit. Of course, on ISS, they have the lids, docking ring. We thought about this way back in 2009 when we conducted the last Hubble servicing mission. So on the back of Hubble, there is a lids docking ring that was there so that when it is captured in the future, it's got a cooperative interface for robotic capture because we knew shuttle wouldn't be around then. So I think the community is evolving. Your point was a good one, and we've started to think about this.
Quick comment. Yeah, we have commented to his website, but we have not talked with any competitors. Sorry. And if you want, maybe the FAA, following along in the airline analogy, could start those conversations, and the Commercial Space Transportation Office might be a good seated place for those cross-company discussions. Just a thought.
Yeah, and I'm going to go back to what I said before. The satellite operators are interested, but what happens when the satellite operator goes to the manufacturer and says, will you do this or you do that? They say, okay, write me a check. Nobody's going to write a check. Nobody's going to make any changes to their satellites until somebody's up there. When somebody's up there providing the basic service, then is when you're going to start to see the sea change. Not one single satellite operator we talked to said that they were willing to pay the money to the manufacturers to make any changes until we have a proven system on orbit. That's the key. We got to get there.
My experience is different.
One way or another, whatever the starting points are, standards and common interfaces are going to be vital to that expansion, especially in space, where issues of power, fluid transfer, gas transfers are going to be vital between common spacecraft systems or different spacecraft systems. So we better get used to that now. Agreed.
Well, we're standing in the way of servicing the audience here. So I wanted to say that this is a really exciting area for commercial space, not without its challenges, but we've had perhaps the best panel we could assemble to address these here today. Why don't you show them your thanks?